Okay, thank you very much for joining us for December 2023 edition of the LINCC Tech Talks. Thank you for joining us for this special time, first day of the month. And today we have the results from our first LINCC incubator. So I'm very excited about that. And the talks will be given by Meg Schwab and Kylie DeSoto. And we will first start with Meg, who is a senior lecturer in the Astrophysics Research Center and the School of Mathematics at Queen's University Belfast in the United Kingdom. She also serves as a co-chair of Rubin's Space and Time Solar System Science Collaboration. Her research focuses on how planets and their building blocks form and evolve by applying ground-based surveys to probe our solar system small body reservoirs. And she will tell us about these efforts and how LINCC interacted with her. Okay, so Meg, please take it away.
All right. Hopefully you can see my screen and hopefully still see my slides.
It's great, thank you.
Perfect. So I'm really excited to sort of talk about our results from our LINCC incubator. And I really want to say that this was game-changing for a lot of reasons. So first and if you hear my cat yowling, she's been fed, she's just old and complains a lot. So if you hear yowling, I promise the cat's fed. Okay, so why is the solar system really interesting with LSST? Well, LSST is awesome. You know that because you're on this call. So you clearly have thought about LSST. But for solar system science, it's really interesting because we're getting the ability to detect order of magnitude more objects, 10-year survey, multiple filters, right? Hundreds of observations per object over 10 years. You get monitoring, you get discovery, and it's an order of magnitude more objects. So it's awesome in all these different ways, between looking at how the solar system changes, right, in terms of transient objects and cometary activity and collisions. It's also really cool in getting physical properties of objects to really probe into the deep details of understanding our solar system information. And so Rubin Observatory is going to provide a moving object pipeline. And so it's going to find most of the objects that are in the images. There are some things that we have to do to look either for the very farthest objects and for very faint ones. But in general, anything that's above 5 sigma in the images, the Rubin Solar System Processing Pipeline will find. And so Mary Urich's group at UW, and also who's part of LINCC, and many of the different direct things that are also going on at UW, is the one that's leading this sort of charge to build the Rubin Solar System Processing Pipeline. So it's like we're getting these objects for free, right? It's a requirement to get these objects and photometry out of the survey, but it's how do we do our science, which isn't just discovery alone. And there's people on this call that do these things far better about thinking about population statistics than I do. But one of the challenges is that there isn't one survey that's done it all. And so one of the interesting things is that often people that study the solar system, if you're doing the outer solar system, the inner solar system is your trash. And so if the objects are moving too fast, you ignore them. Same thing, the inner solar system, you're like, oh, those slow movers, I don't care. And so this is really the first survey in, I think, a very long time that goes all the way out to 200 AU with one detection pipeline that's going to find it all, with one set of systematics, which I think is really exciting, trying to understand the sort of the different populations. And so here I'm just showing, this is the Minor Planet Center depiction of a few weeks ago, but it's showing the blue dots are each a solar system object, and sort of the black lines are the orbits of the planet. So on the left, it's the terrestrial planets on the inside, then you've got the asteroid belt, and then Jupiter, and then on the outer solar system, I don't know why system's not showing, but hey-ho, you've got Jupiter, Jupiter, Saturn, Uranus, and Neptune, and then you've got the Kuiper Belt objects or transinctonian objects. And so the point being is that every object we have, right, we're going to get, 5 million plus solar system objects, and it's one set of systematics, right? And so if people haven't really thought about modeling them as well, think about all of the challenges and things that you have to worry about when you're trying to do a simulation to compare to your observations. And so it's great to have discoveries and know where they are in the sky and have their physical properties, but to really understand how that compares to models and to test or challenge models of our solar system, typically dynamical models that we then have some idea of their physical properties and with associated with those objects. The best thing to do is sort of forward model this and take your model population, create synthetic objects, and then bias it to all the different biases you see in your survey to then look at those simulated detections and compare to what you actually found. Because there's so many different biases of like where the telescope is pointing, right? Again, the limiting magnitude applies to that. Things that are in very eccentric orbits are only going to be discovered for a small portion of the time compared to something that's circular and closer in. The size is going to matter. The albedo is going to matter, right? In terms of, again, whether it's detected or not. And so one of the big tools has been to simulate this, right? And basically you can change any knob in your simulation about your model population and compare to reality, and then decide whether those two populations of simulated detections and real detections are drawn from the same population. And so I know JJ Cavaliers in this call has done a lot to think about this for the outer solar system, right, with the outer solar system origin survey, and before that, the CFEP survey. And so there are sort of simulators, but there isn't one that yet works for LSST and the scale, the number of detections, computing the ephemeris for all of these solar system objects, right, especially with both the scale and the depth. And so the idea is to build this survey simulator, or optimize our survey simulator that we had started to build. And I want to highlight some of the things that you can sort of do with your survey simulator, right? We know that interstellar objects exist. We know that there are comets, but or interstellar objects or interstellar comets, we don't know really anything about the population. And so, if LSST discovers none, you'll be able to use a model of a size distribution and orbit distribution and test how big the interstellar object population could be, that is consistent with not finding something. Or if we find lots of things, right, understanding what that population means and its properties based on thinking about what the full population is, the true population, beyond just what we can detect. And so with the survey, right, it's the power of both what we find and don't find, right? And that's why survey simulation is really important for that. Same thing, we want to explore the intravenous object population. There's one object, Actylodochanum, is the one sort of object inward of Venus's orbit. And so, LSST is going to put really great limits on that population. And so again, to understand the size distribution or the size of the population, it's really helpful to be able to, again, use survey simulators to take the power of both what we find and don't find. Same thing about testing Planet 9, whether it's real or not real, whether if it's not directly found by Rubin or not, if we don't see it, you're going to want to be able to take all the outer solar system detection or the lack of them and be able of things that are beyond sort of the control of Neptune, and be able to compare those objects to see whether we see an asymmetry in the orbits, which is predicted by Planet 9, or again test whether we should have seen the damn thing, as some of the predictions have. And so survey simulators are really powerful in that it touches a lot of different sort of areas of science, different populations, and this is just a small subset. And to highlight something that one of my students has done, but this is Laura Buchanan, who's now a LSST Canada postdoctoral fellow in Victoria. She was using the Outer Solar System Origins survey simulator to take this color population, so G minus R, R minus J here, so again, optical and sort of the slope for the near infrared for outer solar system objects, and sort of try to compare to migration models for Neptune. And so she was taking the sort of planetesimal disk, coloring them sort of whether they were redder or more neutral colored, and then throwing them through Neptune migration and comparing what the simulator said the outer solar system origin survey and the follow-up color survey should have found, right, compared to the model, and looking at whether it could be ruled in or ruled out. And so these are the things you can do. It's really powerful with sort of simulation. And same thing, we have questions about Neptune Trojans, right? So these objects of one-to-one mean motion resonances with Neptune that we think got swept up during Neptune's migration. And so there's arguments over the fact that the one or two sort of reddish objects or very red objects are at high inclination. So we have inclination versus G minus R color. And so it's not clear if there's some correlation, right, with inclination and your G minus R color. And so this is things you can test, right, because Rubin's going to get a lot of Neptune Trojans and be able to test whether that's actually true or it's just an observation bias because we don't have that many high inclination objects or low inclination objects as well, right? And so is it just we haven't found them, or is it a real thing? And so what my group has been building for, it seems embarrassing to say, 4 years or 4.5 years, is Sorcha. And so Sorcha is our solution to how the hell are we going to do this for LSST. And we want to do this in Python because I don't know Fortran. And so Python seemed the way to go, given all the LSST code was in Python. And so the idea with Sorcha is to create sort of a survey simulator that could do handling all the special things about LSST, plus handle all the different things about your different populations, so that you didn't have to worry about running a different survey simulator for your near-Earth asteroids because they're moving so fast compared to if I was doing a Planet 9 population or looking at colors in the Trans-Neptunian region. And so we've been building this for a very long time. But really, the bulk of sort of energizing and optimizing this came over the summer. And so this is the team, especially including our LINCC framework incubator developers. So Drew, Max, Jeremy, really sort of imbibed this project, right, and got us to a point where it could basically get over the finish line. And so we had something that kind of worked ish, but was incredibly slow. And so I'll talk a little bit about that in a second, but I want to highlight what actually Sorcha now does. So Sorcha is it can take a whole sort of population of solar system objects, whatever orbit format you want, but it takes sort of the inputs from the survey, the metadata of the survey effectively. Right now we're using the Rubin simulations, but hopefully, fingers crossed, soon when there's actually data, we'll switch over to allowing the ability to actually read in, one of the either there will be a pointing database or be able to access the Rubin Science platform to get the correct metadata for the observations. But right now, we can take the Rubin simulations, right, of the number of observations and the cadence of the observations and the limiting magnitudes and conditions and the rotation of the camera, et cetera, sort of that's running in the simulation. And then play it forward effectively, taking our population of objects and throwing it through. And so we handled the camera footprint. The fact it is weird, right? That we do handle the fact there's chip gaps and that it's not a circle, but we can do some approximations as well. The detection efficiency, vignetting, detection, the filters, so dealing with colors, and even just dealing with processing both the data management pipelines that do detection in one way, as well as the solar system processing pipelines. And so when we take in a whole bunch of small body inputs, so we take orbits, we take physical properties in terms of colors, phase curve properties, the absolute magnitude, because it's a proxy for size by, it's the apparent magnitude of taking your object and shoving it one of you from the Earth, one of you from the sun. So, it's better sometimes than dealing with albedo, but hey, if you have your albedo and your size, you can convert to H. We also have some ability to do a deal with cometary activity, as well as handle rotational light curves. And I should say, this is the icing on the cake bit that was like, I would love to have seen, and we sort of kind of had, but by having this injection of software engineering time, was able to allow other people on the team to be able to sort of complete these. And so we have the ability to add rotational light curves and cometary activity. And if you don't like our prescriptions, you don't have to use them. We have the ability to basically allow you to import your own base class to this without having to do much more effort. And so if you don't like our prescription, you can change them to whatever you want, which I think is really nice, that if you want to do something else for cometary activity or rotational light curves, you can do it, which is sort of beyond what I thought we would get in version 1 of Sorcha. I thought that was going to be like 3 years from now. So the idea is you can prescribe sort of every which way things about your small body population, plus the metadata for your survey, and then we, are off to the races. And so we split into different files. We could take an orbit file, the pointing database from Rubin Sim, the physical parameters, the H, the colors, the phase curve properties, et cetera, as well as, again, the optional parameters for, in this complex physical files, for your light curves or for your cometary activity. And if you don't like our ephemeris generation, you can provide your own. Or if you want to modify our output to have significant non-gravitational effects, you can do that and ingest your own. The idea is it's basically ingesting all these things and then outputting what LSST would find. And we've made this pretty modular. So the idea is you can turn things off and on. That may matter. We handle trailing losses, so objects are moving very fast, or the ones that are moving fast, right, are going to trail over several pixels. We handle that difference in detection. And I should say that kind of especially matters in the detection efficiency because the way that data management is actually detecting objects is sort of means that we lose some of the sensitivity of the trail. And so basically the object appears fainter than it really is in the data management pipeline, so the signal to noise is less. And so we actually count for that fact that our trailed sources will have some loss in detection due to the way the template matching is done in data management. So we handle all the complex things, including vignetting, right? And then we get out to our simulated population. And really, this incubator has been really helping with our phenomenon generation and really just cleaning things up and making it efficient, allowing us to be able to sort of make something that I think is actually a usable package that might be right. And one of the nice things is that we have configuration files, so you can change things, you can turn off and on some of the filters for detection. If you don't, right, you want to see what happens if you worry about chip gaps or not, we can show you all of that. So I think the beauty is that depending on the population, you may need some things very calculated very precisely or not. We allow that ability to be able to turn things on, turn things off, specify what phase curve function you want to use for solar system people that know what that means, and then prescribe things for our phenomenon generation. And so what was really important, I think, about this incubator was that we were able to sort of inject this ability to take the scientists who can code kind of well. We have some people that are very good at coding in the collaboration, but they're still astronomers that program for the most part. And really having software engineers that could quickly optimize things that we hadn't optimized in Pandas, as well as particularly free up the people to think about the things that were hurdles for us, including phenomenon generation. I'll talk a little bit about that in a second. But it allowed us to get things that were even like really super special into this that I didn't think we would. So we handle the camera footprint. You can either specify it as the full circle of sort of going bigger than the 3.5, or rather using the 3.5 degree field of view, or actually do the full footprint. And so this is showing you that of taking all the sort of detections across all of one of our simulations and aligning them, thanks to Jake Kurlander at UW. And so again, you can see we're reproducing the full camera. And then thanks to Jeremy, again, who leads sort of the engineering side for all of LINCC frameworks, right? We got even more specialized, which is that particularly at the edges of the detectors, you won't be able to detect sources within a pixel or so in. And so if you're doing really slow moving objects, you might kind of care about that. And so we actually have that now implemented as well. So this is a little bit more extreme case, but it's showing the sort of this image before, but overlapped with now our new filter that you can turn on to worry about edges and only focus on whatever sort of inward box within each of the detectors. So we now have these things, depending on your science cases, how accurate you need to get in terms of the footprint. If you're worrying about a fast-moving asteroid, maybe you don't care about gaps. If you're doing slow-moving objects, maybe you care about detector chips. And if you're looking for things at 2000 AU, maybe you actually care about whether it's sitting in that sort of edge before going into the gap. So the ability is we have these things to turn on and be pretty fast. Okay, so those are kind of the highlights of things that Sorcha can do now. I should also say it takes all orbit formats. So if you like barycentric orbits, you like heliocentric, we do both. We take Cartesian, Keplerian, cometary orbits. So it's whatever format you like, which is nice. And of course, Cartesian. And so DP0.3, which is the solar system simulated data products for Rubin, was run with a really old now version of Sorcha. And it took 1,000 cores and over 3 weeks to run the entire sort of asteroid belt, TNOs, a bunch of comets, and some interstellar objects. 3 weeks, more than 3 weeks, at 1,000 cores. Now we can do that 260 times faster. And so on 1,000 cores, we're done in an hour. Less than that, we're done in, and that's doing everything, right? In 2 hours or a couple hours, depending on your machine. And so we have a new improved phenomenon generation from Matt Holman. He was able to basically spend time to make the scheme using his assist and that which calls the rebound integrator and his assist package to basically now predict where everything is and sort of pick out within a circle, a large circle, the things based on sort of integrations per night or stepping per night where the objects are, to then do finer integration and determine which ones are actually within the given pointing of the survey or the simulated survey. So that was one of the big game changers. And that the idea was that Matt just came in with a notebook and was like, this is the rough sketch. And, you know, Max and Drew sort of went in and was able to sort of rip everything apart, shove in this new code, optimize it, and get it to work. Where that's not something I think, you know, a really skilled postdoc that does astronomy, that programs well, can do. And so it's really having this expertise come in and really quickly be able to do the software engineering that really got us the speed. The fact is it allowed other people on the team then to think about adding the different orbit formats and things that they're good at in their expertise of knowing planetary astronomy really well and astrometry, et cetera, and orbits. And so that was really the impact, was that it was freeing these people up to do, right, the experts and the astronomy experts to think about the things that they're good at and allow sort of bring these things together in optimizations from the software engineers. Again, we got efficiencies in pandas because we use pandas, which is maybe a bad decision, but it was like, that was the thing that everyone was like using a few years ago. Might not have been the best choice, but the idea was that we didn't have to rip it out because Drew and Max found all these efficiencies. And again, it was like cleaning up the repository, better setup of our continuous integration. We had it, but it wasn't kludged together. Same thing about the documentation, auto generation. So there's really these combinations of both sort of the sort of basics of software engineering and package development that was helpful. Having people that know how to do this and are not trying to learn it at the same time, that was incredibly helpful. And so I should say is we basically have a full package now that can deliver, runs fast. I create DP 0.3 now almost daily, or my group is. So we went from 4 weeks to we can do it daily. We're still under development. We're basically crossing our T's and dotting our I's to ensure that all of our calculations and filters are correct. We're finding a couple things now that we can actually run on scale all the time. You find all the edge cases. So validation is nearly complete. And based on this incubator, we already have 6 publications that we're planning in various stages as a result of getting Sorcha up to speed. And so it will be open source. I would say don't use it quite yet because we're still sort of tweaking and sort of, again, validating everything. We're pretty close, but it's still probably going to take a month or 2 to finish that. But we went from sort of something that was kludged together and worked-ish to basically a complete package that I'm confident in, that's quick, easy, and I think it will be used, hopefully have quite an impact because it's easy to install, conda and pip installable, and the config file makes it pretty easy to use with the documentation for new grad students, as I'm finding out in my own group. So I guess I should just say thank you to the Link frameworks, because this has really transformed this project and has really taken it from something that maybe was going to get over the finish line in a year or 2 to really over the finish line and beyond what I would have expected in Sorcha in the next few years. So again, thank you to everybody. And that's me.
Thank you very much, Meg. Call in with appropriate animation in the background. Thank you very much. Okay, so we'll hear talks from Kylie now, and then we'll have like a joint question session after. Okay, so Kylie will talk about the other incubator just very briefly. So Kylie De Soto is a graduate student researcher at Harvard Smithsonian Center for Astrophysics. She earned a master's degree from Penn State and did her bachelor at MIT. And as I mentioned, she will tell us about her work on developing machine learning software for supernova classification. Okay, so Kylie, take it away.
Thank you. Let me share my screen. Okay, awesome.
Looks good.
Everyone see this fine?
Yeah, great.
Perfect. Okay. Hi, everyone. Today, I'm going to be talking about this very cool package that we worked on during the Link Incubator project called Superphot Plus, whose goal is to classify supernovae in preparation for LSST. So before I start, I want to thank the Link Frameworks team because they really brought this project from a very bare bones, undocumented code base that would probably not have had a very long lifespan to a full-fledged package that will probably be relevant at least into the first few, if not many more years of LSST. So I wanted to start with some background, talk about what a supernova is and why it's important to be able to classify them quickly, and just talk about the potential of this Superphot Plus package. So what is a supernova? Supernova is a dying star. So here I have a quick diagram of some ways that you can get a supernova. They're very interesting objects because they're these very high energy laboratories in space that tell us a lot of things, from cosmological expansion to the lifespan of stars and the distribution of stellar populations, as well as heavy element generation. And we get two different ways that we can get a supernova. The first comes from low to medium mass stars, such as the sun, or main sequence stars. And we see that as these stars run out of fuel, they die out, they become a red giant, eventually become a nebula, and then when they use all their fuel, they become this degenerate white dwarf. On the other hand, we have high mass stars, which when they run out of fuel and collapse, it's a lot more violent. And you get this big explosion in space, so bright, it outshines entire galaxies, and you get what's called a supernova. This is specifically called a core collapse supernova. But if you go back to the white dwarfs shown on the right for the low mass stars, those can also supernova eventually when they accrete mass from a binary companion. So already just with these very two broad distinctions, we have two classes of supernovae with very different progenitor processes that we ideally want to distinguish between, because if we confuse one for the other, we may derive some wrong physics. So we want to be able to say, okay, if I look at this very bright object in the sky, is it from a white dwarf? Is it a thermonuclear supernova? Or is it from a high mass star? Is it a core collapse supernova? And it actually gets much more complicated than that. There's actually a pretty significant breakdown between types of supernovae based on not only how they exploded, but the composition of the star and its envelope before it exploded. So within thermonuclear supernovae, we mostly just categorize them as type 1a, so white dwarf, binary companion. There's not a lot of diversity. But within core collapse supernovae, which hold a lot more interesting physics, in my opinion, for stellar populations, there are more variety. So for example, if you have a star that retained its hydrogen envelope before exploding, that would be a type 2 supernovae, and its spectra would show strong hydrogen lines. On the other hand, if the star was stripped of its hydrogen or helium envelope, you would get a type 1bc supernovae, and that would look a lot different. You would have weak hydrogen lines or non-existent hydrogen lines, and you would have, in the case of 1c supernova, you would have no helium lines as well. And you can see that on the left in this image. So traditionally, we classify supernovae by looking at their spectra, because their spectra are very clear indications of what physical processes are happening under the hood. And I wanted to go quickly over the 5 main types of supernovae, because this project will label every detection as one of these types of 5 supernovae. So I talked briefly about 1a supernovae, type 2, type 1bc. We also have these rarer types, which are a little bit harder to distinguish. The first of those is a type 2n supernovae, and these are core collapse like type 2s, but they interact with the median around the star before they finish exploding. So that's called the circumstellar matter, and that can influence how the spectra looks as the explosion passes through that matter. We get very narrow hydrogen lines. That's what the N stands for, is narrow hydrogen. And we can learn some very interesting properties about circumstellar matter by studying type 2n supernovae. And then the second rare type of supernovae we cover are superluminous supernovae. And those are distinguished by being very bright. Their progenitor process is still unclear. People think they can come from magnetars. There's a couple other theories with CSM interaction. But essentially, they're 10 times brighter than our other supernovae, at least. And that is how they have traditionally been distinguished. Unfortunately, that assumes that we can determine the absolute magnitude of these explosions. And since we're working with space and we may not always have redshift or distance estimates, it's hard to have a clear classification for what a superluminous supernova is without that absolute magnitude, which makes it a very interesting supernova type to study in this project. So the last thing I wanted to note is on the left side, you'll see that the distribution of these types are very uneven in practice. So most of the supernovae we observe are type 1a because they're bright. They're consistently bright. They're used as standard candles, actually. So we see a lot of them. On the other hand, within the core collapse supernovae, which makes up about 25% of what we see, most of those are type 2 supernovae. The rest are seen a lot less frequently, and as a result are very sought after because there is a lot about them that we don't know yet. So we want to be able to not only classify things correctly, but we want to prevent contamination from type 1a supernovae into all our other data sets, so that we can have strong population studies about type 2n supernovae, type 1bc supernovae, type superluminous. So until now, I was talking a lot about spectra, and how we use spectra to decide what kind of supernovae we're looking at. Unfortunately, that doesn't scale well in the era of Rubin. So right now, we can spectroscopically follow up on about 1,000 to 2,000 supernovae per year with our current resources. And that is about 20% of the supernova-like transients that ZTF detects. So ZTF is a wide field survey. It is the Zwicky transient facility, so it allows us to catch a lot of supernovae every year. Rubin is essentially a very scaled up version of that in the sense that we will detect 100 times as many supernovae as ZTF does currently. So we expect to detect about 1 million supernovae per year with Rubin. Unfortunately, the spectroscopic resources, at least within the first few years of Rubin, are not going to keep up with that. So instead of being able to get spectra for 20% of our supernovae, that drops to about 1 or 2%. So if we rely on taking spectra of supernovae to figure out what type they are, we're going to miss most of them. So what is the alternative? The alternative is just using the brightness measurements directly over time. So we call those light curves. They're essentially brightness of either in fluxes or magnitudes of a light curve over time. And using these light curves, if we make enough measurements over time, we can see the supernovae brighten during the initial explosion, kind of peak and then decline. And the shape of those supernova light curves depends on what type it is. But it's not as strongly correlated as the spectra, for example. So if we say something is a type 2 supernovae and we say it's because it has hydrogen lines, we can't actually translate that directly to a light curve because we don't have that kind of resolution. So it's an open problem whether we can successfully classify supernovae solely based on their light curves. Adding to that, because Rubin will rely on a lot of photometric redshifts, which are not always reliable, we aim to classify supernovae without spectra and without distance measurements. So in the case of superluminous supernovae, that's extra difficult. So that is the problem that we have right now. And that is the problem that Superphot Plus tries to solve. So Superphot Plus is the package that the LINCC framework team worked on. It's an end-to-end package that first imports supernova light curves, fits those light curves to a specific model that I'll talk about later, and then uses those fit parameters to try to classify the light curves. It is inspired by this original package called Superphot, which does something similar, has the same functional fitting form, but Superphot is too slow to keep up with with expected Rubin data rates. The fitting process is on the order of 20 seconds per light curve. We cannot take 20 seconds per light curve if we want to follow up on 1 million supernovae per year. On top of that, there were a lot of improvements that we wanted to make in terms of evening out the data set because it's so imbalanced. There's pre-processing improvements we wanted to make and classifier improvements we wanted to make. So the goal of Superphot Plus was to take Superphot and make it ready for Rubin. And that is what we did. So the main contributors for this package are, you see me, you see my supervisor, Ashley Villar, and you see a lot of people from the LINCC Frameworks team. And together we were able to take this package from a couple of not documented files to a full-blown pip installable, well-documented package, which I think was very impressive in the 3-month time span. So I'm very grateful that we were able to complete that. Yeah, so next I wanted to talk about how Superphot Plus actually classifies supernovae. And it does this in a 3-step process. First, it gets the light curves. It has to get it from an alert broker, so either LSST or Antares. It has to import that data. It fits the light curves. You can see in this image here, that's an example of the model that we use, and we can see that it can fit most supernova light curves fairly well. And then finally, we get those fit parameters, we train a classifier, and we classify those light curves. And what we hope is that most light curves that have a spectroscopic label of a certain type are also classified by our classifier as that same type. So that is what this confusion matrix, which I'll talk more about when we get there, that's what that shows. So we want to import the light curves, fit them, and then classify them. So I'll go through those step by step. The first part about getting the data, we get light curves from either LSST or Antares. So Superphot Plus has files to do either because people have their different preferences. And we have a whole code suite to perform pre-processing to those raw light curves. So what does that mean? So the light curves come in magnitudes usually, which are essentially a logged form of the brightness. We want to convert those back to fluxes, to calibrated fluxes. So our package does that very cleanly, and it does a lot of the pre-processing using a custom light curve class. So that stores the raw timestamps, it stores the fluxes, it stores the uncertainties, and then from there, it has all these built-in class functions to convert magnitudes to fluxes, to apply extinction corrections from the Milky Way, and from the Milky Way, any dust that may be absorbing certain light as the light reaches our telescopes. It performs data quality cuts. So for example, if we want only light curves with at least 5 data points in each band, for example, to do further studies or to do further fitting, it's very easy to do that with Superphot Plus. We can say, okay, only give me light curves with 5 data points with this SNR. Yeah, so that's what this section of the code does. It also does this very interesting light curve clipping that I want to talk about from the image on the top right. So a lot of light curves in ZTF and especially Rubin are not properly, either they're not properly flux subtracted, or there's these long tails as a result of forced photometry or as a result of just taking extra data over time, where there's all this excess data outside of the actual light curve, and that can really influence fitting. It can make fitting very wrong because our models have exponential decay and don't know how to actually handle these very long flux tails that are offset from zero flux. So we perform this light curve clipping to effectively remove all these tails, which significantly improves fitting compared to Superphot. We also introduced this custom survey class, which was very helpful. Basically, you can define a survey called ZTF, and that will keep track of all the filter wavelengths for ZTF. It'll keep track of all the corresponding extinction coefficients. And if we have certain fitting priors set for fitting based on those filters, it will also store that information. So we went from something very, we basically converted Superphot to something very object-oriented and something very modular, which makes it convenient because let's say we want to apply this to Rubin data, we can just define a LSST survey object, and that will store all the filter information, all the extinction coefficients for Rubin, and we won't have to change anything else about the code. We'll just plug in a new survey object, a new light curve object, and the pipeline will be exactly the same. So that was very valuable for thinking forward. Yeah, so after we import the data, we do the actual fitting. So the empirical model that we use is shown in this equation here. It's a piecewise function, which makes fitting a little bit trickier because a lot of gradient descent-based optimizers struggle with that, with piecewise functions. Additionally, there are joint parameter constraints that we had to impose to make sure that the piecewise transition looked physically correct. For example, if we don't impose any parameter constraints, we can end up with a case where we have a piecewise function go up, go down, and then for the exponential decay portion, actually have a derivative going the wrong way. So instead of looking like that, it looks more like an inverse relation. And if you don't impose these joint parameter constraints, the fitting algorithm will do whatever it can to make the best fit, which isn't always physically justifiable parameters. So joint parameter constraints combined with piecewise functions means that we have to turn mostly to Bayesian sampling techniques, such as nested sampling, such as variational inference. And historically, Bayesian sampling techniques are slow. So we end up with this problem. We want something very fast, but we want something correct. And a lot of effort was put in by the team to achieve both of those goals simultaneously. So we actually explore 5 different sampling algorithms, all of which are present in this code base. So you can choose whichever one you want to use in practice. We include nested sampling from the Dynasty package. We include SVI and the no U-turn sampler from NumPy-Row, which is a JAX-based package. So it can optimize using all that cool JAX vectorization. And then we also use series, which is a gradient descent-based algorithm. And we also use migrad, which is the algorithm that is used by, I want to say CERN, for a lot of their fitting. So we studied all 5 of these algorithms, and we see on the right, we compare their runtime, we compare how well they fit, and we compare how many times it fits very, very badly. So how often is the fit completely obsolete? So as you can see on the top panel, nested sampling is faster than nuts by almost an order of magnitude. It takes a few seconds per light curve. SVI and migrad takes less than a second per light curve, and series goes almost instantly. But if you look at the next 2 panels, you'll see the series runs almost instantly because it usually fails to fit most of the time because it can't handle joint parameter constraints. We also see that migrad struggles about 50% of the time, also because of the joint parameter constraints. When we didn't have those joint parameter constraints, both of those actually performed very well and very fast. But again, we need those constraints. So unfortunately, those are not optimal for the problem. Drawing our attention to nuts, nested sampling, and SVI, though, they all perform pretty well. So they do fit most light curves correctly. Nested sampling does the best. So for training, we chose to use nested sampling. So that's the default in the package. But for real-time classification and fitting, we recommend SVI because it can keep up with Rubin data streams at its current rate. And it's only bottlenecked by one-time compilation because we used all that JAX optimizations. So the more light curves we fit in series, the faster it is effectively. Next, classifying light curves. So we explored 2 main types of classifiers here. The original Superphot used just a random forest. We explored something called a gradient boosted machine, which is essentially a random forest, but better. It has an extra residual calculation that it computes every iteration, so it's essentially just a better random forest. And then we also explored something called a multi-layer perceptron, which is what we visualize when someone says neural network. It's just a bunch of layers that are all connected to each other, and there's all these trainable weights to get from layer to layer to layer. And when we fed in our fit parameters from the previous step, and we did this training, and we accounted for class imbalances by doing some fun oversampling, we found that both performed state-of-the-art, but gradient boosted machine did a little bit better. So I want to draw everyone's attention to this F1 score at the top. That is a trade-off value between how accurately each class is classified, and also how pure each classified data set is within each class. So for example, looking at type 1a supernovae and type 1bc supernovae, we see that they're both classified with high accuracy within each class, but we see that 9% of 1a supernovae were labeled as type 1bc. So because there are fewer type 1bc supernovae, that's actually a very significant leakage into the classified 1bc data set. So for example, 195 true 1bc supernovae were labeled as 1bc, but 433 type 1As were labeled as 1bc. So most of our 1bc data set, what the classifier returns as a 1bc data set, is actually true 1As. So we want to reduce that leakage as much as possible because it has a very significant effect. And that's what the F1 score does. It's a trade-off between the completeness and the purity. And we see that the gradient boosted machine has a slightly higher F1 score than the multi-layer perceptron. So for publication, we choose to use gradient boosted machine statistics.
It will be good to conclude in the next couple of minutes.
Okay, we'll do.
Yeah,
Yes. Yeah. So we classified 3500 ZTF supernovae with this trained classifier, which is very exciting. And if you see on the plot on the right, we see that our photometric data set, once we correct for biases, aligns closely with the spectroscopic class fractions that we expect. So that is very promising. So finally, is Superphot Plus good? In short, yes. I think it is very good and it should be used. So it returns state-of-the-art accuracies across all classes with and without redshift information. So the top left confusion matrix is without redshift and the bottom right is with redshift. So obviously superluminous supernovae were classified better with redshift information. Superphot Plus fixes a lot of the fitting issues that were present in Superphot because we put so much effort into prior selection and these nested sampling techniques. So we see that Superphot in yellow completely fails to fit this sparse light curve, but Superphot Plus does. We also compare our results to Parsnip, which is a non-parametric classifier, so it's able to capture a lot of secondary features that our model can't. And we find that our redshift inclusive class version of Superphot can keep up with Parsnip, which is also redshift inclusive. So because Parsnip does not have a version that does not use redshift information, we argue that Superphot Plus is the best option if we don't want to use redshifts. Finally, Superphot Plus outperforms LSST, which is the only other major redshift independent classifier running right now in real time. And we see that it has better performance and it significantly does better at not overclassifying stuff as superluminous supernovae, which is a big issue with LSST. It labels a lot of obscure light curves, a lot of sparse light curves as superluminous by default, and Superphot Plus fixes that issue. So just to summarize, Superphot Plus, it's fast, it's modular, it's very well documented, and it's pip installable. Hint, hint. I've included the code base if you want to install it and use it on your own. And just looking at the plot on the left, this is the performance, the classification accuracy as a function of phase, and it's a good argument that Superphot Plus can work in real time, which is the ultimate goal in the age of Rubin. We aim to set these up as filters on the Antares alert system so that it can classify supernovae in real time for both Rubin and ZTF, which will make it very valuable for future population studies. And the paper is nearing submission. So I'm very excited about that. So most of the figures in this presentation were taken from the paper. So when this is published, I recommend everyone take a look because a lot of work has gone into it and it's very exciting. So so thank you again to the Link Frameworks team for making this all happen. I've included some fun commit plots here to show just how much time and effort has gone into it in the past over those 3 months. And thank you.
Thank you very much. I must say, it's almost like we planned the summary. That was very good. Excellent. Yeah, that was really to the point. Yeah. Okay, lovely. Okay, we have time for questions now. Okay, while we wait, maybe for the first one, I was wondering, Kylie, you would get alerts from Antares and LSST, and like, is there a reason for those two in particular? Is it an ease of use, or do they give you some additional, why those two are not out of all the 7? Let's put that in that way.
So I think I chose those two because of ease of use. They have very, very well documented Python clients, which makes it easy to import light curves. I think it also just happened. I happened to choose LSST and Antares because I was already working to set up Antares brokers. So I already had a desire to use Antares data to make sure that it worked with the filter and all that. And also because I was comparing results with LSST, so it made sense to import LSST light curves. The package is created in a way that if you want to import from any other data broker, it's essentially one function you have to write, a custom function for that alert broker, which makes it flexible if people wanted to import from other brokers.
Thank you. Okay, Nabel, please.
Hi, thank you for the really nice talk, Kaylee. I was wondering, have you explored at all like changing the configuration of the classes? Like, for example, if I was interested in finding only type 1b supernovae or type 1b or 1c, could you set it up so that it was like a binary classifier and you selected only those and you rejected others? Could you get better performance like that?
Yes. So in the paper, we actually looked into binary classification. So between 1A supernovae and all core collapse supernovae. And we saw that there is slightly improved performance versus just collapsing a 5-class confusion matrix. If you retrain for binary classification, the performance is comparable with a lot of other binary classifiers. So it's not really tailored for binary classification. We also explored rock curves for all the different classes, and we found that different confidence cutoffs are optimal for different classes. If we wanted a high purity sample of different types of supernovae. So I think it can be adapted well. It's just not, I think it boasts higher, like it thrives more when we I think the best way to say this. It does better compared to other classifiers, the more classes it has to distinguish between. So let me put it that way. Because the fitting is so nuanced, it's able to capture a lot of shape variations between, for example, type 2s and type 2Ns, or 1As and type superluminous better than other classifiers can. So I think it's the best classifier for that. I haven't compared directly binary classification performance for all the different types. Yeah.
Very cool. Thank you.
Yeah.
Meg, I noticed when you were talking about, you mentioned in one sentence how data management, how they process the data, you mentioned they lose trails of the sources, so they look fainter than they should be, and you need to account for that. Could you a little bit elaborate, like your understanding of that issue? Yeah.
Yeah, so the idea is that these things are like a streak, right? But that's not actually what the filter matching is doing in data management.
Right,
and so it's looking for something as a PSF. And so solar system processing does it right and gets all the flux, but data management doesn't. And so when it goes, this is a 5 sigma detected source, it doesn't go, if I add up all the pixels in the trail, it's 5 sigma. And so you can add it as basically another trailing loss, right? It was sort of or basically a loss in magnitude. And so we calculate the effective point source magnitude that your trailed source is. And it actually really matters, because in DP 0.3, there was the issue of there was an odd offset in phase curves, and it's because and so what was being calculated, what was input into the simulation, the values for the phase curves versus what they were trying to fit and modeling them, and from the magnitudes that they were getting out of the simulation don't match, and it's because of that trailing loss. And so none of us thought that main belt asteroids, it would matter. It's going to be the near Earth objects. It actually is it's significant enough that there's that difference between those two. And so solar system processing will calculate the right magnitude, but to actually figure out what things data management is going to send over to solar system processing, it matters. And so it's sort of it took a while to wrap my head around that there were 2 magnitudes, and that they were different. And so we can deal with that. So, and it matters if you're doing, for inner solar system objects. It doesn't for outer solar system, you can turn it off, but we found out it's so fast, you can just leave it on for everything. But we handle those subtleties that I think you really have to understand data management, it's pipelines to understand. So that was an interesting subtlety that we had to deal with. And then pops up in DP 0.3 of us being it really matters which magnitude you use, and not to use that data management reported one from the initial sort of source detection, but from the trailed source photometry that solar system processing will do.
Wonderful, thank you. Okay, we have a couple of more minutes, so if there will be questions, that would be very nice. Kostya, please.
Hi everyone. Thank you, Kaylee. It was a pleasure to work with you. And my question to Meg, because I know you project better, Kaylee. Like maybe a naive question, could be used for non-LSST surveys, maybe for Roman, for Euclid, for some other kind of survey?
Yes, it needs a little bit of work, but we designed it in mind that the idea is to build on top of it. So everything's modular. So every filter, every calculation we do is its own function, easy to sort of fork off and pull something else. So it would take work, but it wouldn't be impossible to basically switch this to something else. And so 80%, I think, of things would still be there, right? You might not have to deal with the trailing losses because of your sort of the way Rubin's doing its photometry and the data management pipeline, but you're still going to have trailing losses that change your signal to noise ratio. You're still going to have the vignetting, and so yeah, we don't hard code in the footprint. You can put a different file in, for example. So it takes a little bit of work, but the idea is we built the framework that it should be easy. And if I could get funding, I would want to include some of the surveys, like the outer solar system origin survey combined, like they built that they're pointing some things that we could do a dual LSST, right, constraints plus their constraints, but need money and time to do that. But yeah, that's the plan. So it's doable. I think it would take some effort, but good PhD student thesis, right, out of trying to combine surveys, for example. So we've definitely tried to keep that in mind. But right now it's sort of fully set up for LSST, so it would need a little bit of work, but that's the whole point of having config file and different command line arguments, is that we can change those things. So yeah, we've tried to not hard code in where we can the Rubin stuff.
Okay, wonderful. Thank you both. I wanted to just remind you, so the next month, which will be January, we won't have a talk because it will be overlapping with the American Astronomical Society conference. And many of us will be there. There is a special session from Schmidt Futures, who funds the LINCC project. It will be on Tuesday from 2 to 3:30 Central Time, New Orleans time. Philanthropic support for risk in transformational science. So if you're there, I highly invite you to come and join us and talk to us. And then we'll be back in February. Okay, thank you, Meg. Thank you, Kylie, once again. Thank you all. And see you in January and then in February again. Thank you.